Hi all, myself is Nitin. I am a master student at TU Kaiserslautern. Welcome to our presentation on bidirectional typing for Erlang. Outline of the presentation. First, we discuss about the lack of static type system in Erlang and previous attempts to retrofit a static type system. Then we'll compare and discuss some examples. Then introduction to bidirectional typing. Then result and conclusion followed by the future work. Erlang is a dynamically typed language by design, and Erlang programs are not type checked at compile time. So, due to this lack of static type system in Erlang, it is not possible to catch type errors. For example, the type error shown in the example where in numerical value 42 is added with the string. This will not catch at compile time, but it will cause a runtime exception while running this code. So catching these type errors at the compile time is the major motivation to introduce a type system for Erlang. Next, we will discuss about some of the main attempts to introduce a static type system in Erlang. The first one is a type inference system based on subtyping. Since subtyping allows for more flexible programs, and most importantly in Erlang, the terms can belongs to multiple types. The subtyping fits. So this the main idea is based on solving the typing constraints of the form U is a subtype of V. Their approach was not adapted since the system was slow and the infer types are complex, and it did not cover concurrency. For example, here is an example of AND function. Here the second argument is inferred as false instead of binary, like a Boolean type here. So another one is a dialyzer, which is based on success typing. Dialyzer is a discrepancy analyzer which finds all kind of discrepancies, but mainly the type errors. Its main property is no false positives, and it assumes that a program is well typed unless it can prove otherwise. It is the most successful type system and widely used by Erlang community. Success type approach makes it easy to integrate into an existing code base. Here is makes it easy to integrate into existing code base. Here is an example of length function for a list. With the success type, the return type of infer type is coming as any instead of a instead of a number. Most people coming from Haskell or like Hindley-Milner type system, this success type inference may be like a counterintuitive to them. Another one is like Erlang type checker etc. This is based on Hindley-Milner type system with overloaded data constructor for supporting the case where Erlang terms can belongs to multiple types. This Hindley-Milner type system approach was like has faster type checking, and it has like comprehensible type signature and better type errors. By their system, they were able to come up with a statically typed subset of Erlang, which is very similar to Haskell. The problem, like one of the drawback with their approach was that some already existing program may have to be modified to fit into their type checking system. For example, some cases we have to introduce algebraical data type and change the code according to that. So here is some of the dynamic behavior of Erlang. For example, this function list to tuple. The output type of this function depends on the the values in types on depends on the values in the list. So other function like element or is tuple are the same. The output of these functions depends on the values passed to that function, and these types are formed at dynamically formed. The types output of this like dynamically formed, and we need like dependent types to type check these kind of dynamic behaviors. And this makes the like introducing a static type system to Erlang a difficult task. Here are like few example we compare with dialyzer, etc, and some cases where dialyzer misses some type error. For example, this is a case like where in the line number 7, the lookup function will return the value 1 is a numeric, and we are matching it with a string, and dialyzer fails to catch this type error because the function of the type signature of lookup is returning a type any. So a string can be matched with any, and it won't throw any error at like line number 7. And while we run this program, it will crash at runtime because we are matching a string with a numerical value. So this is how etc try to find this error. We have to modify the code. We will be adding an algebraic data type maybe, which has two constructor, none and okay, and we will modify the code to return none and okay, like okay, and we will change the code to match with the okay string to the value returned by the lookup, and here it can catch those errors. Another case is like polymorphism. Here the map function like take a function of type A to B and another list of A, type A, then apply that function A to B to each element in the list given list, and return a list of type B. But here is like the type inferred by dialyzer for the map function. It return like it's accept an any function, like it returns the list of any, and it fails to keep track the polymorphic relationship, like the polymorphic relationship within the function signature. In that case, like we can call an boolean operating function on like a list of integers, and this will crash at the runtime. Another case is like higher rank polymorphism. Erlang allows higher rank polymorphism where polymorphic types occur anywhere in the type signature. For example, here the like polymorphic identity function is only inside the like the quantifier will be only for that polymorphic identity function inside as an argument. The problem is like Erlang type checker cannot type check this because it's not supported the higher rank polymorphism. Same with the dialyzer. Dialyzer also like infer the type, but it fails to infer the higher rank to polymorphism shown as like the type specification we shown here. So it's like the Hindley-Miller type system or like any other type system can like the inferring a higher rank polymorphism is like undecidable. So both dialyzer and etc cannot infer higher rank polymorphism. They cannot support inferring higher rank polymorphism completely. So that's why we were introducing bidirectional typing, which we will make use of type annotation to help the type inference. So bidirectional typing combines both modes of typing, type checking as well as the type inference. In type checking, we will take an expression as well as the type as input, and we will verify the given expression as the given type. In type inference, we will take an expression as input and we will infer the type of the expression and return that inferred type as an output. In bidirectional typing, we are combining this like the advantages of both type checking and type inference. And this bidirectional typing can support advanced programming features such as high rank polymorphism, subtyping, and dependent types. So it is syntax directed, and we only needed type annotation at top level. We don't have to add type annotation for each variable or something. We just need to give the type annotation for like top level functions. So it's very helpful, and we can use this for type system where like annotation type inference is undecidable. Or for example, like the higher rank polymorphism. So here is like few examples of bidirectional typing judgments. It is like a variable. So as I mentioned, there are two judgment, like type checking as type inference. Here, like we have a variable x, and that variable x has a type a in the context. Then we will just simply infer that okay, that variable x has a type a. Another case is like lambda abstraction. So we have like a abstraction lambda x and lambda x that argument x and body e. Here we are checking that lambda abstraction has a type of function type a to b. So to check that, like we know that okay, with the assumption, with the information that the argument x has that type a, we will check whether the body e has the type b. In other cases, like we may not know, like if we want to infer that this abstraction has like a to b, we wanted to like add a type like a placeholder for that type of the argument x. Then we will do some unification. When we get more information, then we can like infer the type to a to b. Here we don't need any unification at all, because we know the both the argument has type a and the function body has type b from the like type annotation. Another case is like application function application, where like both the type inference and type checking judgment both are being used. Here, like we are applying an expression e1 to e2, and we infer the type of e1 as a to b. Then we check that okay, the expression e2, the argument e2 has the type of a, which is the argument type for the inferred function. Another case is like a subsumption rule, where like if you want to change the direction, whereas like okay, we want to check a particular expression e is the type b, we will infer the type of that expression e, and then we check that okay, inferred type is at less than like subset of the type we provided to check against that expression. So far we saw the simple bidirectional type judgment without polymorphism. When we encounter the polymorphism, we are using algorithmic bidirectional type system for higher rank polymorphism, which is proposed by Dunfield and Krishnasamy. The main idea is ordered context, which contains all the like binding, including type variable, term variable, and existential type variable, which is used for partial type information or informations on quantifiers of the polymorphic functions. Also, ordered context is used as input and output to capture the information increases on this existential type variable. Another one is like application judgment. So this is to like we saw that both inference and checking judgment, this is something new, like application judgment to handle the application of polymorphic functions. So here like we are applying that term of type a, which is like a polymorphic function, and after the application of that type to a term e, the resulting expression has a type c. So basically the quantifiers in this quantifiers in the polymorphic function will be instantiated exactly when the function type needed to be revealed. So after the like introducing, and we were able to implement a prototype of a bidirectional typing for some small subset of Erlang, and we were our like bidirectional typing subsumes Hindley-Milner type system, and it supports union type, higher rank polymorphism. Only we require like we make use of top level type annotations. We were successfully applied our prototype on like 3 standard library modules. I would like to emphasize that we didn't modify any user code. We just have to added 7 top level type specification to help the to help the type inference and type checking. So comparing with the already Erlang type checker, the performance is like same time took is almost same, and we didn't have to modify any user code. We just have to reuse the existing type specification, or like we have to add a type specification. Here is an example of like we are using an already existing type specification to check a function which returns a union type. In case of etc, we have to they have to add an algebraic data types to support this case. Here is another example. This delete with friend function is like a private function which is not exported, and we to type check this thing, because since this function returns union of boolean and list, we were able to add a type specification and then able to type check this function. So the limitations are, as I mentioned, the initially the dynamic type behaviors of Erlang is like challenge and like limitation with the current type system. Uh, Another case like future work is like right now it's only for like a subset of Erlang. We wanted to extend it to the whole Erlang syntax, and we want to add subtyping for the built-in types. For example, positive integer is a subtype of integer. All those built-in subtyping relation has to be uh, captured and like supported. Then the records are not supported, and partial evaluation, like in etc they use partial evaluation for this dynamic type behaviors, and it's another possibility to support and these dynamic behaviors if we have like information available at static time. Another one is like concurrency and message passing, which is not supported yet. Other thing is like type checking the legacy code. Right now, like we all modified the code to add the type specification, which may not be like possible in some other cases. So another way to just, if you are not just modifying the code, like another like files or something to just to specify the type specification for legacy code modules. Any questions? Thank you.